Hello and welcome to another CS200 mini lecture. Today we'll talk about chapters 13.1 through 13.8, which deal with recursion. Let's get started. By this time in your computer science studies, you should be familiar with what an algorithm is. It's a sequence of steps for solving a problem. And keep in mind, there's a couple of important things in this definition: sequence and solving a problem. For example, they create lemonade by adding sugar to a pitcher, adding lemon juice, adding water, and stirring. So those are 4 discrete steps that are needed to make lemonade. A recursive algorithm is one that breaks the problems into smaller subproblems and applies the same algorithm again and again to solve the smaller subproblems. The example they use has mowing a lawn. So you mow the lawn, which is the problem, and then the subproblems are mow the front yard and mow the backyard. We break it into smaller parts, so instead of just mow the front yard, you mow the left part and the right part. And again, you could probably break it down further and further. We'll look at some real world recursive problems, and we'll see how this can be done. One important thing that we have to remember is there's a point in which the recursive algorithm has to know when it's done. Otherwise, it will run infinitely. And that's a big problem when we're writing an algorithm that's recursive. So we have to know when we reach the base case. So a recursive method is a method that calls itself again and again. And remember, a recursive method has to know when to stop. In Zybooks, they have an example of a countdown timer. I've made some small modifications to it, and I've put it into BlueJ. So let's take a look at it there. So this is our class called countdown timer. So we have a method called countdown, which takes one parameter, countInt, and it just makes a simple branch statement. So if countInt is less than or equal to 0, we know we're done. Otherwise, what we're going to do is we're going to print out the value of the integer, and then we're going to call our method, but just pass it whatever that integer is and subtract 1. So it's going to keep running until we hit the case where countInt is less than or equal to 0. And then in our main, all we're doing is we're passing countdown and a value, for example, 10. So instead of go, which they have in the Zybooks, I put blast off. So when I run the program, what I expect to see is it counting down from which value we had, which is 10, down to 0, and then when it hits 0, we're going to say blast off. So why don't we see a 0 here? Let's go back and take a look at the code. Going back to the code, we can see that we never print out the value 0. The reason is because when we're here, we're making a comparison against 0. We don't print out the value, we just print out blast off. And this makes sense because when we see a rocket take off, we don't see them go 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0 blast off. Well, maybe if they were computer science students, they would. But typically they go down to 1 and say blast off. So there's a couple of important things that we need to realize when we talk about recursion. There's 3 laws. So all recursive algorithms have to obey these important laws. First of all, we have to have a base case. Second of all, we have to make progression towards that base case. And last, we have to call ourselves recursively, meaning we call ourselves. This is the code we just saw. I took this from BlueJ. So this is the code that does the countdown timer. It starts with 10, goes down to 1, and then the word blast off appears. So this is our base case. That's when count equals 0. And if we have that situation, we have blast off. So this tells us when we stop our progression and we stop making recursive calls. We also have to have a recursive call. So this is where we actually do countdown, and then we pass the value -1 recursively to the same method we have. So that's the countdown method. And we're also making progress towards the base case because we're calling recursively the same method, countdown, but we're passing a value that's 1 less. And eventually you can see we're going to get down to our base case, which is where countin equals 0. So in this case, we've met all 3 of those important laws. So here's a recursive challenge activity that has us going backwards through the alphabet. And we're going to start and pass in a value, and we're going to go backwards until we hit A. Let's take a look at this in BlueJ. So this is the same code that we have in the challenge activity. You can see here that I've added some comments. So if the current letter equals A, this is going to be our base case when we reach A. Because remember, we're passing a value like D, and it's going to go D, C, B, A. So we have to tell it when to stop. So what we're going to do is stop and print out the letter. Otherwise, what happens is we're going to print out the current letter plus a space. So what happens if we only have an A, it's going to just print out the letter. If we have a B or any letter that follows A in the alphabetical order, what's going to happen is it's going to print out that letter and a space and keep calling itself, and it's going to reduce the letter by 1. So here's our progression towards that base case. So when we make the call, we prompt the user for a letter to start at, and what happens is we can use ch13 to make sure that we don't have any other values. Like, so for example, I type A space, it's not going to mess up our system. It's going to take the first letter that I type. And here is our recursive call. This is the initial call. And then it calls backwards alphabet, which goes and calls itself again and again and again. Okay, so let's see it run. So here it prompts me for a letter to start at. I'm going to give the letter T. And you can see here it starts with T and calls the recursive algorithm over and over again until it hits A. So what happens if we just use A? It should already know how to stop and just prints out the A. So that gets us to the base case in 1 step, whereas if we do T, it requires quite a few more steps. Again, these are recursive calls. One of the benefits of recursion is the simplicity. Think about what you'd have to do if you had a problem like this where you had to write the alphabet backwards. You're given a letter and you had to go steps backwards. It'd be a lot of code. Maybe you'd have a case or a switch statement for all the different letters that are possible, and then you'd print out, for example, if you put a B, you'd put BA. If you had C, you'd do CBA. Could you do this? Yes, but it's really ugly code. Recursion doesn't really save us some time. In fact, when we get to 13.8, we'll see that it actually can cause some problems. However, recursion is an elegant solution. So again, there's nothing that can't be done using other methods that we do with recursion. It just helps with allowing a very tight, concise way of solving certain types of problems. Not all problems can be solved with recursion, but many can. So there's lots of ways in which we can use recursion. One is to do a search algorithm. So for example, with binary search, and again, when you get to CS301, you'll look at different types of search algorithms and sorting algorithms. But binary search is one in which you're trying to find a number in a sorted order. Again, it's important that it's sorted because we're going to make comparisons based on position. So we can find a value in the least number of steps. And it's actually very efficient as you learn more and more methods. So you have a friend, and your friend's thinking of a number, and they're playing the warmer, colder, or higher, lower game, and their number happens to be 32. So you prompt them, say, give me a number between 1 and 100, and I'll try to guess it in as few steps as possible. So what happens is they guess right in the middle. Because it's a binary, you're going to know to go left or go right. In this case, we happen to go lower. So the next step is to have that window. Now we have our window between 0 and 50 based on the input your friend gave, and we're going to do 25. So the next step is we tell your friend says, oh, it's higher than 25, and then you repeat the process and narrow it down. So you can guess a number, in this case, in as few as 4 different guesses. Let's take a look at this in BlueJ. So here's our code. And again, this is taken right from your book. But all we're doing is we're making a recursive call, and we're getting a response lower, higher, or yes, we got the letter. So what is our base case? Our base case is when we have yes, which means the input's not lower or higher. It just basically says we got yes as the answer. So that's when we know to stop. Otherwise, we have to make a recursive call. In our recursive call, we pass 3 values. We pass the scanner object, but before that, we pass the low and the middle value. Otherwise, we're going to pass the middle value and the higher value. So for example, the number 32, the first time we call it, we're going to pass 0 and 100. Okay, so when we get 0 and 100, and why do we pass the scanner object here? It's because we're going to get repeated input from the user. So we determine a middle value, and that's going to be the high and low value. In that case, it's 0 and 100 divided by 2, which is 50. And then we say, is 50 the right answer? And then we get a response from the user. And then if it's not yes, then we're going to get the input and make a determination of which direction to go based on that. So if it's lower, we're going to take the low value, being 0, and the mid value we calculated, which is 50, and then we're going to go and we're going to call it again, which is going to change the middle value to 25. And then we're going to ask, is it 25? And then we're going to get a response and keep going. So let's play the game. So I'm going to use the number 45. That's my secret number. So they're going to say, is it 50? And I'm going to say lower. And they're going to say, is it 25? And I'm going to say higher. Is it 38? I'm going to say it's higher. Is it 44? Oh, we're getting close, because you can see it's dividing between 38 and 50 in half. 44 happens to be the number. I'm going to say higher. 47. Is the number 47? No, it's lower. And you can notice it keeps dividing number. Is it 46? It's lower. Is it 45? Yes. So it might be interesting to see what happens if we tell it it's not 45, what it would do. So again, lower, higher, 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 lower, lower, lower. And see, it just keeps repeating because there's no other values to create, so it's going to keep using the same numbers. We could also recursively search a sorted list. Notice the keyword sorted. So if there's no ordered to the list, it's going to be very difficult to search because, for example, in the numeric example, we had 0 to 100, and we make the assumption that those numbers are sorted because typically that's what we look at with numbers. But if we had a sorted list, things might be different. So in this example, we have a list of names, and we're trying to find that person's name. So let's take a look and see this in BlueJ. So this is the same program that we saw in the actual zyBooks. And what we're trying to do is we're trying to find and match in an array list a set of names or a name. So first of all, we have to have our base case. And this is essential. If we don't know what our base case is, then we're not going to be able to have a very efficient, in fact, we can't have a recursive algorithm that's going to stop. So this tells us when do we arrive. And then we have two different base cases, right? Either we find the item or we don't find the item. And then the recursive case is to keep going and search. So here's our main, and there's our list. We're going to add a bunch of names. We have to remember what these names are. And then we're going to prompt the user to find a name. So here we have enter a person's name. And of course, since I don't know these names, I'm going to go back here and cheat. I'm going to say Domer Hugo. And of course, it tells me the position it found it. Now, if we rerun the program, and we give it a name that is not found, it tells us that it's not found. Again, with the base case, it either finds it in the list or it finds that it's not there. Here's a challenge activity that I'm going to skip. However, I strongly encourage you to look through it and make sure you understand those three important laws to recursion. Now, one important thing to note is a lot of times we want to make sure we're going towards that base case. So if we want, we can add some output statements for debugging. Again, output statements are helpful when you're writing code and you're trying to figure out what's going on because it allows you to see what those variables are. So they make the suggestion that we indent and we actually print out values showing what those items are. So let's do this. Let's take this and go to BlueJ. And again, we can look. And you can see here, this is output that we didn't have in that original run. Now running it again, you can see that it does. By doing this indentation, which is what the book is trying to illustrate, you can see when it's making another recursive call. So it keeps making these recursive calls, and then it basically puts the call onto the stack. And we'll see this in chapter 13.8. And it keeps pushing it down on the stack until we get to the base case, and then it starts popping off the stack. So it passes these values -1, which indicates that it can't find that item. Now remember what's important. We need to have that base case, and that might be the best place to start when you're writing a recursive method. So what they suggest is when you write a recursion, you start with the base case. So you can put a fix me in for the non-base case. That's when we're making calls to our method recursively. So in this case, we're going to start with the base case because once we get that down, we know we're going to need it. Now we make a copy and we think about the recursive case. When do we make another recursive call to the same method? And also we have to remember we need to make progression towards that base case. So in this case, they're doing a factorial. So you'd pass in a number, and then it would be multiplying the number you pass in times every value less than that number. So for example, 6 recursively is 6 times 5 times 4 times 3 times 2 times 1. 1 is the base case, so that tells us when to stop. We don't stop at 0, we stop at 1. Mathematically, if we multiplied by 0, of course that would give us some issues. Here's a challenge activity that you might want to consider. I'm going to skip it, but it's one that I would suggest you try if you're having or you're struggling with knowing what is the base case to write. Recursion is used a lot in math. Doesn't mean it's only used in math. It just means that math provides a lot of examples in which recursion really works and works well. The Fibonacci sequence is one where you start with 0 and 1, and the pattern is to compute the next number by adding the previous two numbers. So you start with 0 and 1, you add them together, the next number is 1. 1 and 1, it's 2, and so on. So the Fibonacci sequence is one in which you can build upon, and it continues forever. So what is the base case? Base case is if you have a number that's 1 or less. Otherwise, what you have to do is you have to compute the next value. This is one in which, so let's take a look at it running inside of BlueJ. So I'm going to put 10 as the number of steps I'd like to see. And you can see here, it does 0 and 1, which are the first two inputs. And we finally get a number of 89. Now we could make a very large number, and there's kind of a danger to this, which we'll see here in a couple minutes, and that's we'll have issues with Stack Overflow. But one thing you can notice is it's actually very elegant how this is done. And if you appreciate writing code that is very concise, yet very meaningful and poignant, then understanding how recursion helps resolve a Fibonacci sequence is quite good. Another problem is the greatest common divisor. So a greatest common divisor is the largest number that goes into two numbers. So for example, the greatest common divisor of 2 and 4 would be 2. Let's take a look at this in BlueJ. So we have GCD Calc, and this is one where we take and look at the greatest common divisor between two numbers. So this method has two parameters. It takes two arguments that are passed in. They're actually the two numbers that we want to check and see. Now, why is this recursive? Because we're going to call this repeatedly as we try to define and get larger and larger numbers. So again, we have to have our base case. So our base case is what? The numbers are equal. So if I pass in 4 and 4, the greatest common divisor is going to be 4. Otherwise, what we have to do is we have to do a comparison between the two numbers. And if the first number is larger than the second, then what we do is we call it with new values. And the new values here illustrate what they are. Let's take a look. Let me run it. So I'm going to give the numbers 108 and 16. And it says the greatest common divisor is 4, which makes sense. Let's take another set. Let's say 32 and 12. It also says 4. Let's say 111 and 55. So no common divisors there except for 1. And let's run it one more time. Let's say 24 and 32. So we're convinced that it actually works, because 8 would be the greatest common divisor between those two numbers. Another class of problem that's solved by recursion is looking at all possible values, or permutations. So here's one in which we can choose different letters. So we choose the first letter, the second letter, and the third letter, and then we come up with these different permutations, 6 different permutations from 3 letters. So those are all the possibilities that can be made with those 3 letters. So believe it or not, for a problem this simple, it requires quite a bit of code. So we have to think about, what is the base case? The base case is when we've used all the possible letters. Otherwise, we have to add another letter, just like we went down the tree, and come up with another set of values using that particular letter. And then we go recursively through the length of the letters. So if we have 3 letters, we're going to go through 3 different ones, and we're going to scramble them. So we have to use each one of those and recursively call it with every possibility. So if we run this program, we could have a word to be scrambled. Let's just say we use ice. Let's do it short, just so we can see all the values. But here's all the possible letter combinations, the permutations that can be done using the letters ICE. If we do something much larger, we can see that it'll be much more challenging to come up with all of them. So here's all the ones for the letters of alphabet. And again, just like we saw with other kinds of values like factorials, the recursion is one in which we can look and see that as we add one more letter, it adds to the complexity of what we're trying to do and makes it run longer. So in the last problem, when we had the letters, we had a couple of different things in which we could do. First of all, we could go and look through a dictionary and see if any of those letter combinations would actually match another word. And then we can see if we can use, for example, the word ace, we can see if they come up with any other words that use the word AC, that comprise of the letters A, C, and E. We could do that by doing a dictionary check each time we came up with a combination of letters. Here's another problem in which we have a shopping spree. We have a bunch of different items, and say we want to maximize the price. So we're allowed 3 different items, and we want to try to maximize the price or minimize the price of the items that we could have in that bag. So we come up with every possible combination, every permutation, and then we can check to see if that value is greater or perhaps less than all the other values we've calculated so far, like a minimum and a maximum problem. So again, in the Zybooks example, they don't do that second part. They don't compare it to see which one's the minimum or the maximum, but you could see how easily that could be done by adding another method. I'm going to skip over the shopping spree combinations. However, it follows much like we saw with the letter combinations, just looking at ways in which we can combine items in different permutations and then come up with some kind of solution, which is our base case. Here's one that's actually a pretty famous problem. It's called the traveling salesman problem. In this case, we're going to start with just 3 cities, and then we have distances between the cities. And we may want to perhaps minimize the distance. Say we have a traveling salesman. He wants to try to minimize the distance between 3 cities because it saves him time. We'll just make the assumption that he's driving or she's driving, and this will make it much more efficient if they're able to organize the cities in a certain order that minimizes the distance. It may be a maximization problem If, for example, we want to boost the number of frequent flyer miles and we're flying between the cities. So there's different ways to look at this problem. When we get to a larger number of cities, in this example we're using 3, but when we get to 10, 11, it gets to be a very complicated and cumbersome problem. And it becomes very, very slow to run this problem, but with 3 it should run pretty fast. So let's go to BlueJ and take a look. So in BlueJ, we can see here that we have a couple of public static variables. We have the number of cities, which isn't going to change. And where does that get declared? What part of memory? Just as a reminder. And then we also have a multidimensional array of integers, which compares the cities, and then we have the city names. So what we're trying to do is we're trying to look at the distance going through a path. So if we have cities like Boston, Chicago, LA, there's different ways in which we can calculate the distances. And again, in this distances array, what we're doing is we're just looking at the distance between 2 cities, and we're trying to look at the comparison. So that's like an arrow between different nodes or an edge. So we have actually with 3 cities, 3 nodes, we're going to have 2 edges. So what we want to do is we either want to minimize or maximize the distance between them. Typically it's a minimization problem, but let's take a look. Let's run this. Now when we run it, we don't prompt the user for any values, so the values are already set. And you can see here that the values that we get are the combination of 3 cities, and we could easily parse through this and find the minimum or the maximum values, and that might be the suggested route for the user. Now, as promised earlier in this lecture, one of the problems we could have is stack overflow. Remember, each method call places a new stack frame on the stack. So what happens is we have to place it on the stack, and it only gets popped off when we have got to the base case. So it's very possible that we could have a stack overflow. And that's when we have more recursion calls than we have stack space. Let's take a look at this example. So we have an initial call, and we have another call. We keep calling it. And then if this is the end of the stack region, we're going to run out of space, and we can't pop off the values of the stack because we haven't got to the base case yet. So we just have to be careful that we could hit stack overflow. Let's go back to the case of the recursion problem in which we had all the letters and the combinations. We could possibly, even with as many as 20 letters, blow out the stack. If you recall, one of the problems we had was factorial. That's where you're multiplying 1 times 2 times 3 up into the value we want. If we get a number that's like 1,000 factorial or 2,000 factorial, we could easily blow out a stack depending on how much memory has been allocated for the stack. So in recursion, we have to remember a couple of things. We have to identify a base case. We have to be able to reach that base case too. So we have to make progression towards that base case by making recursive calls that move towards that base case. We saw some examples in which we would reduce the call by 1. We saw others in which we would branch out and try to find make sure that it's between 2 values and narrowly go towards it. We saw others that we would give every possible combination. We'd know we'd hit the base case when there were no more left.